Hello, class. So on the previous video, we finally saw how to use basically as calculus and a little bit of physics to come up with a model that gives us the velocity of an object at a given time t that's falling vertically. So I came up with this model here, the last box in orange. Now I mentioned that this is a differential equation, right? Because we have, I'm just going to write the model here again. We had m times so the mass times the velocity of the object equals negative the mass times the acceleration due to gravity plus a proportionality constant times the velocity. Now let me say that this constant k, as I said, it's just a proportionality constant. Sometimes it's called the drag coefficient. So k is sometimes called, but for us, it doesn't really matter. We know where this came from because we derived the model ourselves. We know this comes from air resistance. Okay. So now we have this model, which is a differential equation because it has a derivative of v with respect to t. So what's the solution? A solution is a function v. Then when we plug it in, gives us equality on this equation. So whatever's on the left is equal to whatever's on the right. Now, as I mentioned in the previous videos, we have a general process to find a solution to a differential equation. You integrate both sides. Now here, we can't actually work with this model as it is yet, based on the techniques that we have, because since we don't know what v is, right? V is what we're trying to find. We don't know what v is. So when we go to integrate this right-hand side, how do we deal with the integral of kv? And again, the independent variable matters. So we took derivatives with respect to t, so we want to integrate with respect to t. Well, how do we find this integral? We don't know what v is, so there's no way to actually do it. So this is why, with the techniques that we have right now, we can't actually find a solution to this particular model. If we simplify it, though, we can find solutions. So how are we going to simplify it? So what we're going to do is we're going to assume that there is no air resistance, right? So assume that this is falling in a vacuum, right? So think of a vacuum as something that there's no air, and we have this vertical tube that all that's happening is that this rock is falling down. So the only force acting on it is its weight. Okay? So that's the situation that we're here. If we assume that there's no air resistance, then our model simplifies because with no air resistance, what happens? Well, we know that this was the force that came from air resistance. So that basically goes to zero because there's no air resistance. So our model simplifies a little bit, right? We get rid of that extra kV. Now that's good because that's what was giving us problems before. We couldn't integrate both sides because we don't know what V is. We can't really simplify that integral. So now it's a little bit better. So now that I've said this, let's see what this example is actually asking us to do. Right? So assume that there is no air resistance. Right? So that's what happens. It simplifies our model. So use the model in example 7, this model that we're working with, to find the position, right? So I mentioned solutions to this differential equation give you velocity, but you can easily get to velocity from velocity to position. Okay, so find the position of the object at a particular time t, given that the object has initial velocity 5 meters per second and initial position of 100 meters. So basically, we're at sea level, the rock is 100 meters above sea level, and you let it go. You just drop it and let it go. Actually, you don't just drop it. So let me say, I'll say a little bit about what initial velocity is. If you, in this particular situation that we have, where we have so here's sea level, we have a rock here, and we know that this distance is 100 meters. The initial velocity, what it means is that whoever is dropping this rock here, so say there's someone in so that's a cliff or something, and then this person dropped it, right, dropped the rock. Now, since there's initial velocity, that means that this person didn't just let go of the rock. Okay. In fact, what this person did is he kind of threw, or she is whatever pronoun this person is using, this person pushed it downwards, so kind of threw the rock down with a velocity of 5 meters per second. Okay. So it's kind of like that's what's happening. That's what initial velocity means. If the initial velocity is 0, that means that this person just dropped the rock, just let it go. If there's an initial velocity, that means that this person actually threw the rock, right? So it gave it an initial velocity instead of just letting it go. So think of someone just pushing the rock downwards, so just letting go. That's what initial velocity means. Okay. Of course, initial position is just we're 100 meters above. Okay. So that's basically the setup. This is kind of like the picture for this problem. We have this picture here. We have this model that models this system, and we want to find the position of the object. So we're starting with acceleration. Remember, dv dt is acceleration. We want to get all the way back to position. So we have to do it in steps. We're going to go from acceleration back to velocity, back to position. Okay. So first, let's simplify things a little bit. So let's divide both sides by m here. Because remember, m is just the mass of the object, which is the same on both sides of the equation. Okay. Now, let's go to another slide. So far we have this simplified model. Again, we're trying to find position, which, as I mentioned, we're going to usually denote by S. So S of t is position. V of t is velocity, sorry, as functions of time. That's right, why I write S of t, V of t. And A of t is acceleration. So this is very similar to the first problem that we saw, the first differential equation that we saw, dy dt equals 2. It's basically the same thing. We have a process to solve something like this. What do? We just integrate both sides with respect to t. Because again, that's the variable that we're taking the derivative of with respect to. So we want to integrate with respect to the same variable. So let's integrate with respect to t. And again, whatever you do to one side of the equality, you have to do to the other side. Let's simplify. So the left-hand side, an antiderivative of dv dt is of course just v by definition. And we add a constant. That's what a indefinite integral is. Equals, now negative g is a constant, right? Remember, g is an exact number, 9.8 meters per second squared. So g is just a constant. So if we integrate this, we just multiply it by t. And of course, we have the constant of integration. Like I said before, whenever there's two arbitrary constants or however arbitrary constants there are, I'm usually always going to combine them into one constant. So here I'm going to subtract c from both sides. So combine it with d, and I'm just going to have this constant c. So now what does this mean? Now, given this setup, we have a rock, we let it fall. There's no air resistance, so we're in a vacuum. What's the solution to this differential equation? Well, the velocity of this object at a given time t is going to look like negative g times t plus some arbitrary constant. Now, it would be nice if we could get rid of this constant here. Right? Right now, it's an arbitrary constant. That means that we have infinitely many solutions for this differential equation. Now, how do we get rid of that constant? Well, we can use some of the information that we were given. Specifically, we were given that the initial velocity is 5 meters per second. Now, how can we write this as a mathematical equation? Now, what is initial velocity? That means the velocity right when we let go of the rock. If we think of this model as just modeling, as taking just focusing on the time after we let go of the rock, that means that we can interpret this as at time equals 0, that's when we let go of the rock. And then as time passes by, t increases. And here, let me say that since we're working with seconds, then here our time has to be in seconds. So it's another way we can interpret our model. We can say that we start taking time as soon as we let go of the rock. And then as the rock is falling, we're taking time. Think of taking time with our chronometer. Now, this is useful for us because that means that we can interpret the initial velocity as the velocity at time equals 0. This is, by definition, the velocity when we let go of the rock, which is precisely the initial velocity. And again, like I mentioned, in this case, since the initial velocity is not 0, we're actually not letting go of the rock. We're actually throwing it downward with this initial velocity of 5, as I explained in the previous video. So how do we write this mathematically? Well, the velocity at time t equals 0 is precisely 5. Now, why is this useful for us? Because we can use this information to get rid of this constant c. Why? Well, we know that whatever function we plug in into this differential equation, so there's infinitely many. We know they all have this form, but we also wanted to specifically satisfy this equation, that v of 0 equals 5. So how do we do that? Well, just plug in 0 into the function and set it equal to 5. Right? So v of 0 is negative g. We're plugging in 0 for t. So change every t for 0 plus c. And we know that v of 0 has to be 5. Initial velocity has to be 5. So we have negative g times 0 plus c has to be equal to 5. Well, any number times 0 is 0. So 0 plus c is just c. C equals 5. What does that mean for us? Even though this differential equation has infinitely many solutions, infinitely many velocity functions that satisfy this differential equation, there is exactly one that satisfies this differential equation and this property, that the initial velocity is 5. What is that function? Well, we just found it, right? Is, well, negative g times t plus this specific constant 5. And again, how do we solve for this constant? We use the fact that the initial velocity is 5. We wrote that mathematically and we plugged it into our equation, into our model. So in fact, let me make some sort of divide here. Okay. Now, a property like this is usually called an initial condition. So let me do this here. So v of 0 equals 5 is called an initial condition. Why initial? Well, because it's happening at the start of our model, right? At time t equals 0. Why is it a condition? Because it's conditioning our model, right? You saw this is conditioning what velocity functions can be solutions to this differential equation. It can't be any velocity function, right? We know there's infinitely many that have this form. It has to be the one for which c is equal to 5. This is the only one that satisfies this differential equation and this condition. So that's why it's called an initial condition, because it happens at t equals 0, the start of our model, and because it conditions what functions can be solutions. So it's differential equation. Now, we're not done yet, because what was the question asking? The question was asking for position, not velocity. Okay? So in the next video, we're going to start where we left off here, and we're going to see how we can get from velocity back to position.